All right, in this next video, we're going to look at relative masses of both atoms and molecules. And it's a little bit confusing to think about, but for many years, scientists could only compare relative masses. And let me show you what I mean by that. What they did originally was they compared an atom like hydrogen. So if you look at hydrogen on the periodic table, it's atomic number 1, and then the mass is listed as being 1.008. And then what they would do is they would compare other elements to hydrogen. So for example, if you look at helium on the periodic table, its elemental symbol is He. It's atomic number 2, and the mass was 4.003. So when they compared these, they immediately noticed that every time they did this experiment, that helium is approximately 4 times heavier. So this was how they studied a lot of the elements for quite a while. Was they were just looking at how much heavier one atom was compared to another. In particular, they like to use hydrogen as a benchmark because it was pretty close to being an atomic mass of 1. So they could compare everything else to it and say, hey, if we look at, let's say, carbon's 12 times heavier than hydrogen. And so they always use these comparisons. Today we have a lot more advanced equipment in our labs where we can actually measure the exact mass rather than the ratio. So in particular, I wanted to make a note on that. So today we use what are called mass spectrometers. Oops. To find exact masses and we don't need ratios. The ratios that they used from kind of the early 1800s and on aren't really used anymore because we have such high-end equipment. In addition, the mass unit that is used is called the atomic mass unit. And oftentimes you'll see this abbreviated as AMU, and the unit symbol that we usually see in our textbook is just represented with a little u. So that's something to be aware of. And it's interesting, the AMU units actually have a standard, and that is that one atom of the carbon-12, or of carbon-12, that particular isotope of carbon, is equal to exactly 12 atomic mass units. So this is the standard to which everything else is compared. I know it seems a little bit weird that they use carbon-12 and not hydrogen, but that's just the isotope that they chose to use in this case. All right, now it is a little bit confusing to think about, because when we think about carbon on the periodic table, it's actually listed as 12.01, not exactly 12. So then the question is, well, what's going on the periodic table? And you may notice on the periodic table, they oftentimes have these numbers that go out to a number of digits. And in this case, that's actually due to something called isotopes. All right, so the mass shown on the periodic table it's actually an average. So it's an average mass of an element containing all natural isotopes. All right, this value is called the atomic weight. And this is another trick that I oftentimes show my students is anytime you see the term weight listed, that should immediately spring into your mind that, hey, this is an average. If you see mass listed, then that's very precise. It's talking about the mass of one particular thing or one group of things that are all the same, right? Where weight is basically just saying, hey, this is the average of a big group of different isotopes. Not all the isotopes weigh the exact same, so we're just going to get an average of them. We can do a similar thing with molecular weight. So if we think about the molecular weight, it is also an average. And to find the molecular weight, it's actually pretty easy. So let's take an example here. And all you need to do is come up with some molecular formula. So in this case, it's H2O, it's water. And we'd say, all right, we have 2 hydrogens. And each of these hydrogens, if you look on the periodic table, has a mass of 1.008 U. And then if we look over here, we could say, well, there's definitely one oxygen. And this oxygen has a mass of 16.00, or sorry, I should say weight, average weight of 16.00 U. And if we want to find the overall molecular weight, all we need to do is add this all together. So I could say 2 multiplied by 1.008 U, and then we'll add this into our second part, which is 1 oxygen, which is 16.00 U. And we can find the molecular weight for water is just going to be 18.02 atomic mass units. So in this case, it's pretty easy to find by just using the values provided to us on the periodic table. The other thing that I forgot to mention here is we still have to use our sig fig rules here too, right? So that's why I ended up rounding the way I did, and I don't have that last digit there because of the addition and subtraction rules. So do pay attention to that as you're going through. All right. So let's kind of touch on this average feature, right? Because we're talking about this a fair amount, that anytime we're talking about atomic weight and molecular weight, we're referring to averages. So let's take a look. And I'll use this example with chlorine. So 75.53% of all chlorine is chlorine 35. And chlorine 35, we can find its mass, and chlorine 35 has a mass of 34.97 atomic mass units. Okay, so that's just one isotope of chlorine. The remaining percentage, which is 24.47% of all chlorine that's remaining, is going to be a different isotope. In particular, it's going to be chlorine 37. And chlorine 37 obviously has 2 extra neutrons, which means it's going to have a heavier mass. And in this case, it's going to be 36.97. So it's got 2 mass units higher due to those 2 neutrons. So let's try to calculate what the average mass would be and what should be on the periodic table. So let's do the atomic weight. And in this case, I'm going to multiply the percentage of chlorine 35 by its atomic mass. So I would say, all right, this is 75.53%. In this case, I'm just going to leave it as is and divide by 100 at the end. And the mass was 34.97 atomic mass units. So that's one portion of the natural abundance. And then the other portion we said was 24.47% with the mass of 36.97 atomic mass units. And we'll divide this all by 100. All right, let's zoom out a little bit. When I do the math here, I'm getting 35.4594 atomic mass units. But let's pay attention to sig figs, right? According to our multiplication rules, we shouldn't be left with any more than 4 sig figs there. No more than 4 sig figs here. If we follow the addition rules, it doesn't really change much. So this means our final answer should have 4 sig figs. And that means it would be 35.46 atomic mass units. All right, so this would be the atomic weight, meaning the average of all isotopes, and this would be the number that you would see on the periodic table. But I did want to emphasize this because it is something that confuses a lot of students. When you see the number on the periodic table, your mind doesn't immediately jump to this jumble of different isotopes. You just think, hey, that's what one of those atoms weighs. But it's important to remember that not all atoms of a specific type are the same. We've got a distribution of various isotopes. All right, I hope that helps, but let me know if you have any questions.